Next, we have another highly anticipated segment of this virtual conference. It is now time for us to listen to the first guest speech of the International Conference in Data Science 2021. To introduce the first guest speaker to the audience, I would like to invite Senior Lecturer of the Department of Statistics, University of Colombo, Dr. Rushan Abegunawardana.
Thank you, Sekha. It is my great pleasure to introduce Associate Professor Bimbas Chakraborty to all of you at the ICDS 2021. Associate Professor Bimbas Chakraborty is a tenured professor of the Center for Quantitative Medicine at Duke NUS Medical School, and associate professor at the Department of Statistics and Applied Probability, National University of Singapore, and adjunct associate professor at the Department of Biostatistics and Bioinformatics, Duke University, United States. Previously, Associate Professor Bimbas served as a director of the Center for Quantitative Medicine and as the founding co-director of the PhD program in Quantitative Biology and Medicine at Duke NUS. Associate Professor Bimbas completed his bachelor's and master's degree respectively from the University of Calcutta and the Indian Statistical Institute in Calcutta, India. Subsequently, he completed his PhD in statistics from University of Michigan, United States, under the supervision of Professor Suzanne Murphy in 2009. He then worked as an assistant professor of biostatistics at the Mailman School of Public Health, Columbia University, United States, prior to his move to Singapore. He is the Calderon Research Prizes for junior faculty from Columbia University Mailman School of Public Health in 2011, and the Young Researcher Award from the International Indian Statistics Association in 2017. He has served as a principal investigator of research grant funded by the Ministry of Education, Singapore, as well as the National Institute of Health, USA, in addition to being a co-investigator on numerous grants from various funding agencies. Over the years, he has also served as a scientific reviewer for several funding agencies, including the National Medical Research Council in Singapore, the National Institute of Health, the Patient-Centered Outcome Research Institute in the United States, the Netherlands Organization for Scientific Research, and the French National Alliance for Life and Health Sciences. Now, I would like to invite Associate Professor Bimbas to deliver his speech. My dear friends, please welcome Associate Professor Bimbas Chakraborty.
Let me just first share my screen. Okay, can you see my screen?
Yes, so we can see your screen.
Okay, great. Okay, so thank you for the kind invitation and also for the kind introduction. This is a great opportunity to speak to such an interesting and very curious audience of students, as well as our distinguished speakers and guests. And so, with due respect to the Vice Chancellor, the Dean of Science, the Head of Statistics, Director of Center of Data Science, and other guest speakers, I would like to talk about this topic on data science in mobile health, which I think is a timely topic. This is based on joint works with several people, Some of them are from my own lab, some of my own students and postdocs, as well as some of the external speakers, external collaborators that are listed here. So what is mobile health? Mobile health, or sometimes referred to as mHealth, this is practice of health and healthcare supported by mobile or other digital devices. And the word digital health is also quite common as an alternative. So as this picture shows, mobile phones are everywhere, right? With that kind of penetration in the entire population, mobile and digital interventions has a huge appeal, and it can potentially reduce the traditional health disparity across different parts of the population. And thus it's very useful and attractive from a global health perspective. However, I will move to more technical aspects of some of the mobile health studies that I have been involved with, and associated statistical / data science issues, rather than talking about the more general aspect of its appeal in the global context. So in particular, I will be introducing a novel trial design called micro-randomized trials, sometimes called MRT, that is useful in this domain of mobile health. And this is somewhat different from the traditional randomized control trial that most of you may be already familiar with. And I'll talk about various issues related to such designs. How do you learn from data from those kind of studies? And of course, I will walk you through real examples, real data. Okay. So here is an app, mobile app. Name is Diamante. Diamante stands for Diabetes and Mental Health Adaptive Notification Tracking and Evaluation. So there are many health apps these days that helps you keep track of or manage your health condition. And this is one of those apps. Interestingly, there is also a study with the same name, Diamante. This is led by investigators at the University of California, Berkeley's Digital Health Equity and Access Lab. And this study has an overarching goal to develop, implement, and evaluate an adaptive learning clinic integrated mobile intervention, particularly targeting to promote physical activity among low-income ethnic minority patients who are suffering from both diabetes and depression together. And this is in the San Francisco Health Network. So if we segregate the goals of this study, it sends contextually tailored, contextually relevant text messages, SMS, to the patients to manage their condition, to motivate them, to prompt them to do more exercise, more walking. And these interventions, the messages are multifactorial intervention. They have different components. Another aspect of the study is to learn to send better messages as we go, as the study goes, by continuously learning from the data, adaptively learning from the data. So the study at the broad level, it's a 3-group randomized control trial with inbuilt micro-randomization. And I will come to that in a minute about the micro-randomization part. So at the macro level, there are 3 groups. First is a static messaging group. This group of patients, they receive daily intervention messages according to a fixed factorial design. The statistics students in the audience, I'm hoping that already have heard of factorial designs. If you have multiple factors of treatment, you can combine them together, you can allocate them together simultaneously. And this is an old topic in statistics. Then the next group is an adaptive messaging group. So they also get the intervention messages, but the messages are not the same throughout the study period. Here, there is an inbuilt learner, which learns as more and more data comes along the way and tries to send better messages based on whatever it learns. And the learning is driven by a class of methodology called reinforcement learning from the AI literature. And then the third group is a control group who don't receive daily intervention messages. There is only just a weekly message about, mood and steps. So that's basically the data structure. Here's a schematic of the study design again. Again, on the left box, you see the A, B, C, the three groups. And on the right side, it just shows the flow of things. So you first observe their time varying context, which day of the study, what day of week, whether it's a weekday or weekend, how much you worked previous day, what message did you get yesterday. All these data, time varying covariates, those are collected and made available to the system. And then, there are multiple factors of treatments that are given, which are basically different kinds of messages. I'll elaborate more in the next few slides. But the point is, those messages are given every day. And then at the end of the day, their physical activity improvement is collected, computed, how much steps they walk. And this goes on for 6 months. First factor is the motivational messages factor. And it has 4 levels or 4 categories. Of course, there's a no message category, but then there are other messages appealing to self-belief aspect of your motivation. Some messages talk about the actual concrete benefits of walking. And the last one is about opportunity, about specifically telling that, how you can incorporate your exercise into your day. And this has to be done every day. Otherwise, people forget or people become lazy. So these are the aspects of, tapping on people's motivation or promoting people's motivation. And there are some example messages. I'm not going to read myself, but you can take a look at this, some of the examples. There are many more examples. There are, box of messages that we have. And preliminary evaluation of these messages were performed on the Amazon Mechanical Turk crowdsourcing platform prior to the main study. So this has a background. It doesn't fall from the sky. There has been prior work, more qualitative kind of work, evaluation, feedback to prepare this message bank. And this is what the psychologists in the team, they did. The second factor is feedback messages. Likewise, here we have 5 different levels or categories of messages. Basically, it tells you whether or not you reached your goal yesterday, how many steps actually worked, whether you worked more or less than your target. Sometimes you add a positive or negative message in addition to the step count. So different ways of framing the message, framing the feedback about your performance. Again, that was all tested out before. And then the final factor is the time frame, which time during the day you are delivering the message, whether that has an impact. That is also something that the study team wanted to investigate. Then there's this contextual variables or covariates. In statistics, we call it covariates all along, but sometimes in the data science world, in this kind of data science problems, these adaptive learning problems, we call it contextual variables. So there are all these baseline information plus the time varying variables like which day of the study, how long you have been in the study, or which day of the week, etc. And then the primary outcome is the number of steps walked in the next 24 hours. This is collected passively via the phone's pedometer. So the study design that we considered is a micro-randomized trial I mentioned earlier. these designs are cutting-edge trials that are suitable to take care of this sort of time-varying sequential interventions. And because these are multifactorial interventions, there is this motivation message, there is feedback message, time, etc. So you can think of this as an extension of full factorial designs in a sequential setting. And at each decision stage, in this case, every day, people are randomized between possible options, and each person may be randomized at hundreds of stages, right, in general. And in the study itself, this is a 6-month study. So the actions or treatments or interventions, specifically in our case, the messages, they are intended to have a proximal effect. We don't expect that people will sustain an impact of the message 2 days later. So micro-randomization helps to generate data to assess causal effect of the proximal impact, proximal causal effect. And from a study design point of view, the things that we look at is, the questions that we wonder about is how to study the power and sample size requirement for these kind of studies, particularly with more than 2 levels. And so that's with the basic MRT. But then we also want to know how to best adaptively learn, sort of learning online about more effective messages while in the trial. As the trial goes on, as we accumulate more data about people's performance, people's response to the messages, how can we use that information to send better messages to the other participants beyond that initial group. So here is the data structure formally. It's a little bit more than standard longitudinal data. There are T stages, and the trajectory of data for each individual is a collection of X, A, and Y, 3 kinds of variable, where X is the context or pre-treatment variables, A is the treatment or intervention or action, and Y is the proximal outcome, the steps in our case. And A could be a vector for multifactorial interventions, as in our case, and XT can also be quite high dimensional. So the outcome model for analysis of this kind of data, what is the basic principles that we follow in such data? So we have to keep in mind that the intervention effect is time varying. It's because, for example, with digital kind of interventions, initially we are very excited, and people in general are quite excited with a new intervention, joining a new program, etc. But then initially, for the first few days, they might even struggle to keep track of, or there's a change in their lifestyle, or navigating the technical aspects. So there might be a little bit learning curve initially. Then people are still excited after a few days, and now they are getting it, they can navigate it. So then there is a stable, good period. But then after a while, like all things in life, things lose a little bit of appeal. So people get too habituated and do not really respond. They learn to ignore text messages, right? So that habituation impact and the effect can come down. So there could be a quadratic kind of a trend. This is the time varying effect of treatment. So you have to incorporate that in your model. So even though we can, at the very basic level, we can think of a regression model, the key point here is the regression coefficients will be time varying. It's all indexed by T. So that's the message I want to give you. And then from a power or sample size point of view, if you want to design your study properly, adequately powered, you have to specify what kind of hypothesis testing you're going to do. And for that matter, in this context, it might make sense to consider an ANOVA type global null hypothesis of no treatment effect whatsoever. So you can have this null hypothesis beta 1 T through beta M T, all of them being 0 for all T. And you can, depending on your situation, depending on your specific problem at hand, this is where the domain knowledge will come in. You can and you should specify a suitable alternative hypothesis that you will be using for testing. And in the context of habituation phenomena that I was just talking about a little bit earlier, that initially there might be a learning curve, then a stable period, and then it will go down, the impact can go down. So you can think of those betas, you can postulate the betas to be a quadratic function of time. As I have written here in the equation, beta m0 plus beta m1t plus beta m2t square. Right, so there are other possibilities, of course. This is just one example, how you may want to specify your alternative hypothesis about your treatment effect, intervention effect. Okay, and then analysis involves dealing with longitudinal data, dealing with all these complexities of how you specify the effects, etc., etc. Long story short, we would need to use something like a generalized estimating equation, or GEE, for those of you who are familiar with longitudinal data analysis. So you can use that technique, some extension of that technique, to estimate the effects of the parameters. And for the testing purpose, in order to test that null hypothesis, you would end up, if you follow the technology of all these estimating equations, etc., you will end up with the fact that in large samples, the test statistic will follow a non-central chi-square distribution, and you can use that to do your test, which means you are in a position to study power and related aspects. So I just want to show you some sample size calculation necessary for achieving 80% power to test that global null hypothesis. And here I'm considering m equal to 4, m here meaning how many message categories. And you can vary, of course, all these things will impact how your power and sample size will pan out. But here is some illustration. Some of the input parameters are as usual. Here you have to specify how many decision points, t. The effect size, there are different components. So in a standard randomized trial, you just give an overall effect size. But here we talk about initial standardized effect, average standardized effect, and day of the maximum effect, as there is this quadratic kind of trend of the effect that I mentioned earlier. And of course, you have to specify your desired power and level of significance. And then based on that, the numbers are here. So the first, the first two, second and third columns correspond to the power, correspond to the sample size corresponding to two different standardized effects. And the last two columns are the corresponding Monte Carlo powers. So one thing to note here is that even for reasonably small length of studies, relatively small values of t, even then the sample sizes are quite manageable. This is a big plus compared to traditional randomized trials, because here you have the option to pull across this longitudinal data. You are observing a small group of people maybe, but then you are getting repeated observations from them, and you are pulling information to gain that kind of efficiency, which means it is not so hard to conduct this kind of studies. It's a lot more affordable to do these kind of studies in a particular population. So for example, if someone has done in another country and you want to replicate to your country, this is quite doable and without a lot of extra hassle, or not very expensive, so to speak. Because this expense is a thing that that makes conducting randomized trials difficult, and people have to often rely on observational studies. But then observational studies often come with well-known problems of selection bias and confounding and so on. So anyway, I think this is the moral of the story, that it's possible to do it with a relatively small sample size to conduct such studies. Okay, I'll now switch gear to talk a little bit about adaptive learning that can be done within this MRT setting. And this is what we also have done within our Motivating Diamante study. Remember, we had 3 main arms or groups. One is the control, one is the basic MRT, and then the other one is this adaptive learning kind of MRT, where methodologies like reinforcement learning has been implemented. And what is reinforcement learning, in case you are not familiar? This is actually a technology coming from the AI field. And it's also machine learning, but it's a different kind of machine learning, not the supervised and unsupervised learning. This is something different, where you learn by interacting with an environment. And this technologies has been used in classical settings like robotics and automated flights and games, etc., etc. Specifically in our context, we feel that short horizon reinforcement learning algorithms like contextual multi-armed bandits, or MAB algorithms, are quite suitable. And these algorithms have been used in recent years, for example, in promoting online ads, online advertisements by various websites, Facebook, Google, Yahoo, etc., etc., Netflix. So because when you go to these websites, we feel like they know what we are looking for. How do they know? So they know based on our past behavior of web experience, and based on that they put the right kind of ads that we are looking for. So that same idea can be useful in our mobile health setting, where we have sent certain kind of messages and we have noticed their behavior, how they are responding to certain kind of interventions. So based on that, we can tailor what kind of messages would work or appeal better to them, right? So the same kind of ideas, same algorithms. And in particular, we focus on an algorithm, and in the study we have implemented that is linear Thompson sampling, operationalized via a Bayesian regression. And this is grounded in an old statistical paper back in 1933 by Thompson. But in the recent years, with the emergence of data science, and particularly with these online advertisements and recommender systems, all these things, with the explosion of technology, these methodologies have also gained traction and gained popularity. And this Thompson sampling is a very popular method now in computer science, data science. Oops. Okay. So I'll be very briefly sharing what is a simple operationalization of linear Thompson sampling might be, and particularly what we have worked on in our study setting. So we assume a Gaussian reward model or outcome model. So basically the y given x, a, and the parameter beta. It follows a normal distribution with mean f transpose beta and variance sigma square, where f is a known feature vector, which is constructed based on both x and a. It can have their main effects and interactions, and possibly other nonlinear terms using splines, etc. And we also assume a Gaussian prior for the beta. More generally, one can use Gaussian inverse gamma priors for its, if you also consider prior for the sigma square parameter. And you can then compute the posterior distribution of the beta given all the data till that stage, t, which also turns out to be Gaussian because of the conjugacy properties. And the parameters of that posterior distribution can be computed, because essentially there is a regression going on. So the parameters of the posterior distribution can be computed via least squares or Ridge or Lasso kind of regression, whatever is relevant in a certain setting. And so specifically the TS, Thompson sampling algorithm, involves the following step at any given state, which means at any day as we go along in our study, we observe the XT, all the time varying covariates, all the baseline and time varying covariates that we have. And we also have collection of previous data from previous stages. Based on that, we have to draw a sample from the posterior distribution, call it beta tilde, and it's not just the posterior mean. This is an important point. It's not the posterior mean. It's actually a draw from the posterior distribution, and this is in order to encourage exploration, not so much exploitation of the information. You still keep learning, not just get fixated at the mean. And then you choose the optimal action, in our case, optimal message, based on this maximization of the posterior mean of the predicted outcome. Choose that action, execute that action, meaning send that message, and observe the next stage's outcome and the context, how people respond to that intervention. So in our case, in the Diamante study, the model does that every day, or rather every night. After the day's data are collected, every night it runs in the server, and next day it knows what messages to send. Okay, so that's that. And we don't yet have the final data from that study, but we have a pilot version of it. Here we don't have a control group, but we only have a standard micro-randomized trial arm and another arm with the Thompson sampling. The primary outcome is again daily steps, but it has a shorter duration, only 45 days of intervention. And this is not on the clinical population of diabetes and depression patients. These are only undergraduate and graduate students at the UC Berkeley campus, about 100 of them. And it applies all these methodologies that I have already talked about. So some data. These are the distributions of the step count and changes in step. We see, and this is something that we anticipated earlier, and accordingly we adjusted, but this actually reinforces the understanding that step count would be a skewed variable. So normality might not be most suitable, whereas if you work with the steps change from the previous day, that would be a more symmetric variable to work with. Normality assumptions will be reasonable. And these are the average step counts over days as study progresses, how things happen. So as you see on the left panel, the average step counts slowly decreases. So you might say this is an habituation. This is a habituation effect. People are losing interest or not following. However, when we look at the steps change, it still seems, average around 0 with large variations, of course. Finally, we have analyzed the data, pilot data with GEE. And so the first analysis we conducted is effect of sending any message, right? Does it at all help if we send messages, reminders, motivations? Does it really help? And it turns out that it does. We see a significant effect of sending message, but also we see a negative effect of the interaction between message and the day of study. Right? So this is again the habituation. After a while, as study progresses, the effect diminishes. The next analysis is separately looking at motivational and feedback messages. We see that the motivational messages are actually statistically significant, but feedback messages are not. And then this one is a bit more granular analysis. It looks at the different categories, and we see that certain categories of motivation and feedback are significant or close to significance, others are not. And finally, this one, we look at a comparison between uniform random group, the micro-randomized group versus the Thompson sampling group, and there is no significant difference between them. Although, in fact, to a little bit surprise, Thompson sampling looks slightly in the worst direction, even though not significant. Okay, so comments about ongoing and future work. Of course, the data collection here is not perfect. It can be improved, particularly if we can introduce a wearable device like a Fitbit, etc., instead of relying on a phone pedometer, because people are not always carrying their phone. So some missing data will be there. People's steps will be missed. Model selection, variable selection in Thompson sampling is critical, and just what we saw earlier, that Thompson sampling in the pilot data was not working very well. And one potential reason is that the model that we assumed, the priors and the reward model, whatever we assumed, is not probably optimal. So this is something that there's an enormous opportunity to learn. And along those lines, you have to do a better job at modeling the habituation effect that I mentioned, and how to handle skewed large count data within the Thompson sampling framework in a theoretically solid way. That is also something we viewed as an important future work, because the traditional theoretical work, theoretical statistical kind of work, in terms of probability bounds of these different algorithms, etc., almost all of them are on normality assumptions. What if the data is not normal? We are not so sure yet, and there is not much out there in the theoretical literature also. So some take-home messages. You may forget everything else, but just a few things to keep in mind are these micro-randomized trials that I've just talked about are newer kind of trials in the mobile digital health space. They're very relevant for behavioral or lifestyle interventions. And in a way, you might say that these are old wine in a new bottle, because these are extensions of age-old factorial designs in a sequential decision-making context. Analysis involves longitudinal data analysis like GEE, and you can incorporate these adaptive elements of learning within the micro-randomized framework by Thompson sampling or other reinforcement learning algorithms. So this is an integration of classical statistical ideas with reinforcement learning, which is coming from the AI or more broadly from computer science. So in my view, that's data science, with an understanding also of the underlying domain of psychology and health behavior, etc. And finally, I want to also emphasize the fact that these kind of interventions are relatively cheap and can penetrate across a large part of the population, can help reduce health disparity and appealing from a global health perspective. Okay, here are some of the references. Again, these are all in the medical or interdisciplinary kind of journals, but application of statistical or machine learning ideas in this particular domain of health behavior change. Okay, with that, thank you very much.
Thank you very much, Professor Bibas Chakraborty, for that very insightful speech. And you certainly gave the audience a very thorough understanding about how useful data science and statistics is for different applications in mobile health. It was amazing to learn how the micro-randomized trial can be used for developing just-in-time adaptive interventions, such as motivational messages to exercise more. So thank you very much, Professor.
Thank you.